Welcome back to the deep dive. It is Friday, February 6th, 2026, and I have to be honest with you. I did not get a lot of sleep last night.
You and me both.
Yeah.
But I'm guessing for very different reasons. I was up just running the numbers again.
And I was up staring at the ceiling trying to, keep my existential dread in check because
Okay.
today we're not just talking about some cool new exoplanet or a slight tweak to an old theory.
Oh, this is different.
We are talking about a research report that landed on my desk just 48 hours ago. It's titled Cosmological Architecture of the Black Hole Universe.
It's a dense read, a very dense read.
Dense is, I think, the understatement of the year. It's not just dense. It feels like a rewrite of reality itself. The core hypothesis is something that, honestly, it sounds like the plot of a Christopher Nolan movie.
That's not the same thing.
But the authors claim it's mathematically rigorous. They claim it's fact. And the hypothesis is this. Our entire observable cosmos, every star, every galaxy, you, me, the room you're sitting in right now, all of it resides inside the interior of a short-shelled de Sitter black hole.
We're living inside a black hole.
They're living inside a black hole.
That is the headline. And I know the immediate reaction. I had it too. It's, wait, hold on. Black holes are where physics goes to die.
Yeah.
They are crushers. They are destroyers.
That's the pop culture image, right? When I think of a black hole, I think of spaghettification. I think of being stretched into a long, thin noodle and then just obliterated. I do not think of that.
Of trees.
Coffee, podcasts.
And that's the fundamental misconception this report is trying to dismantle. It argues that the interior of a certain kind of black hole, a sufficiently massive one, isn't a death trap at all. It's a nursery.
A nursery.
In fact, they go further. They argue that being inside a black hole is the only thing that saves us from the biggest crises plaguing standard cosmology right now.
We're talking about the fine-tuning problem.
The fine-tuning problem, the so-called crisis in cosmology, the Hubble tension, the whole shebang. This isn't just a what-if thought experiment to sell some sci-fi books.
No, this is positioned as a solution.
It's a how do we fix the broken math of the last 50 years kind of scenario.
Mm-hmm.
So the mission for this deep dive is to walk through this 2026 report step by step. We have the theoretical derivations, which we will definitely break down, and we have hard data.
And that's the key, right? It's not just theory.
Not anymore. We have data from the James Webb Space Telescope, from DSI, and from the Event Horizon Telescope, all collected over the last 2 years, 2024 to 2026.
So just to set the stage for everyone listening, we have a new theory that says we are inside a specific kind of black hole. And this theory claims it can explain why our universe looks the way it does without needing, I don't know, magic numbers or an infinite multiverse.
Correct. But to even get there, we have to start with the very first objection, the one I saw you scribbling all over the margins of the report.
The mass problem. I couldn't get past it. The bag of gold.
The bag of gold paradox. Let's dig in.
Let's get into this. Because when I first looked at the numbers in section 1, I was convinced it was a typo. I literally pulled out my phone's calculator, thinking the authors must have misplaced a decimal.
It's a natural reaction. Walk us through that discrepancy.
Okay, so we have a pretty good estimate for the mass of our observable universe. If you add up all the normal matter, that's stars, gas, dust, us, plus all the dark matter, and then the energy equivalent of everything else, you get a number.
It's a big one.
It's roughly 10 to the power of 54 kilograms, a one with 54 zeros after it, just a staggering amount of stuff.
Right.
But then the report calculates the mass of the host black hole, the container that we are supposedly all inside of, and that mass is calculated at about 10 to the 53 kilograms.
Something like 5.4 times 10 to the 22 solar masses, yeah.
Which is huge, don't get me wrong.
Okay.
But it is roughly 29 times less massive than the stuff it's supposed to contain.
It creates an immediate, a cognitive dissonance.
Dissonance, it sounds like absolute nonsense. How do you fit a 10-pound universe into a 1-pound bag? My entire experience with packing luggage for a holiday tells me this is impossible. If I try to put 50 pounds of clothes in a carry-on, the zipper breaks.
The zipper breaks, exactly.
And here you're telling me the carry-on is actually lighter than the clothes inside, but it still zips up just fine.
It's the ultimate packing nightmare, and you were absolutely right. In Euclidean geometry, the flat space geometry we use to build houses and, yes, pack suitcases, this is impossible. Volume A cannot contain mass B if mass B is larger than the container's defining mass.
What?
But we aren't in Euclidean space. We're in general relativity.
Space creates the shape.
Exactly. The report brings in this concept of a bag of gold spacetime, which was analyzed pretty heavily by physicists like Marolf and Su years ago. To get your head around this, You have to stop visualizing a black hole as a solid, dense ball sitting in space.
Okay, so what should I be visualizing?
You have to visualize it as a topological shape, a feature of space-time itself. Imagine a throat, a very narrow passage, or a neck. This represents the event horizon of the host black hole, as it would be seen from the outside, from the parent universe.
Okay, so some hypothetical alien astronomer in that parent universe looks at our black hole and they just see a regular old event horizon.
And the size of that horizon, that throat, is fixed by the external mass, that 10 to the 53 kilograms, that determines the size of the door, so to speak.
The door's fixed, got it.
But once you cross through that door, you enter the bag, the interior region. And here is the absolute mind-bending trick of general relativity. The volume inside the horizon is decoupled from the surface area of the horizon.
Decoupled, as in they don't have to match up.
They don't have to scale together in the way we'd expect. The interior space can expand, and I don't just mean it stretches a little bit, it can expand to be arbitrarily large.
So the neck of the bag stays tight, but the bag itself just puffs out
Yeah.
infinitely.
Think of it like a balloon animal. You know how a clown can pinch a tiny segment? That pinched off part is minuscule. That's the event horizon. But the balloon segment on the other side of that pinch can be huge. You can eat the whole rest of the poodle.
Okay, but in this analogy, the balloon, it's made of space itself.
Yes, space-time is the rubber. And because space-time can stretch and warp in these extreme ways in general relativity, you can pack a truly immense amount of entropy and matter inside that bag. The external observer sees a finite black hole. The internal observer, that's us, sees a vast, seemingly infinite, expanding universe.
It's the TARDIS from Doctor Who. It really is bigger on the inside.
Bigger on the inside is actually a mathematically valid statement in curved spacetime. It's not just science fiction. But the bag of gold paradox specifically refers to this fact. You can have an interior mass, or 10 to the 54 kilograms, that is far larger than the ADM mass, the mass that's observed from the outside.
And the gold in the name, that's us.
Yeah.
The matter.
The gold is the entropy. It's the information content. The matter, the galaxies, the stars, us. We are the gold in the bag.
That is a weirdly flattering way to put it, but it also seems to mess with the rules of information, doesn't it? I remember learning about the holographic principle, the idea that the amount of information you can stuff into a region of space is limited by the surface area of its boundary.
That's the standard Bekenstein-Hawking bound, and normally that's a very strict limit. If you try to pack too much information into a region, you create a black hole.
But here we're already in a black hole.
Exactly. So does the limit apply in the same way?
I'm guessing not.
The report argues that this bag of gold topology fundamentally redefines the holographic principle. The information isn't lost, and it isn't just compressed onto the surface in the way we typically think. The interior universe, with all its complexity, its star charts, its history, its podcasts, is the microstate structure of the host black hole.
Wait, say that again? We aren't just in the hole. We are the guts of the hole.
We are the internal configuration. To that alien astronomer in the parent universe, the black hole just has mass and spin and charge. But they don't know why it has that specific mass and spin. The why is us. We provide the internal states that add up to those external properties.
That makes me feel incredibly significant and totally insignificant at the exact same time. Okay, so the bag works. Topologically, the luggage zipper holds because the bag is made of magic space-time rubber.
Essentially, yes. A bit more complicated, but that's the core idea.
But then we hit the next big problem, the math problem, the scaling contradiction. And honestly, this part of the report, it felt like a direct attack on, the last 20 years of theoretical physics on this topic.
It was a necessary correction. I mean, this isn't the first time someone has proposed a black hole universe. Patria and Good proposed a version way back in the 70s.
And Lee Smolin, right, with cosmological natural selection in the 90s.
Right. Smolin pushed it forward in a big way. But all those earlier versions, brilliant as they were, had a fatal flaw in the mathematics. They tried to link the mass of the host black hole, which we call M, to the cosmological constant, lambda, that's the vacuum energy, using a linear scale.
Linear meaning?
Right.
Like a simple one-to-one relationship? If the mass doubles, the energy halves?
Roughly, yeah.
Yeah.
They posited that lambda is proportional to M to the power of -1, 1 over mass. It looks very elegant on a piece of paper until you check the units.
Dimensional analysis, the bane of every first-year physics student's
Right.
existence.
It's the apples and oranges rule of physics. You just cannot equate two sides of an equation if they don't measure the same fundamental type of thing. It's
Hmm.
the most basic check, and the old models failed it.
So what were they trying to equate that didn't match?
Okay, so vacuum energy, lambda, has units of length inverse squared, that's 1 over length squared, or L to the minus 2. But mass, in the geometric units physicists use, has units of length, just L.
So they were saying L to the minus 2 equals L to the minus 1.
Which is wrong. It doesn't balance.
Help me visualize that. I know inverse square is a term we hear a lot, but what does it actually mean physically?
Okay, think of it like painting a wall. You have a bucket of paint, that's your quantity, right? Your mass, and you have a wall.
Okay, with you so far.
The old math was trying to equate the bucket of paint to the length of the wall. Like saying, this 1 gallon of paint equals 10 feet.
That makes no sense. 10 feet of what? A line drawn on the floor?
Exactly. It's a category error. Paint doesn't cover line. It covers an area. You need square footage. You need length times length, L squared. You can't compare a mass to a length. The units have to correspond to the same physical dimension.
So the old theories were trying to turn paint into a ruler.
And that's why they always hit a dead end. They were dimensionally inconsistent. The 2026 report introduces what they call the inverse square scaling law. They derived it from a very specific physical state called the Narii limit. And this law fixes the dimensions. They say lambda is proportional to m to the minus 2.
Mass squared on the bottom.
Mass squared. Now the units match. L to the minus 2 on both sides.
Yeah.
You're comparing, in our analogy, the amount of paint to the area it can cover. The math finally clicks into place.
But they didn't just pull squared out of a hat because it fit right. You mentioned the Narii limit. That sounds like an anime power-up move or something.
It does, doesn't it? But it's actually a fascinating extreme state in this kind of geometry, Schwarzschild de Sitter geometry. To understand the Narii limit, you have to remember that in a universe with dark energy, like ours, there are actually two important horizons.
Two. I thought there was just the one event horizon.
There's the black hole event horizon, that's the inner wall, the point of no return for things falling in. But there's also the cosmological horizon, that's the outer wall, the edge of the observable universe for any given point, beyond which space is expanding away from us faster than light.
Okay, so we are kind of sandwiched between the hole's mouth and the edge of the universe.
Exactly. And usually there's a huge amount of space between them. But if you keep adding mass to the black hole, its event horizon grows outward.
It gets bigger. Common sense.
But here's the weird part. As the black hole gets more and more massive, the cosmological horizon actually shrinks inward.
Wait, what? They move toward each other?
They do. And at the Narii limit, they meet. They merge. The black hole becomes so maximally massive that it effectively fills the entire available causal universe. The two horizons. They touch. They kiss.
That sounds incredibly claustrophobic.
It's the maximal mass configuration. You literally cannot stuff any more black hole into that patch of de Sitter space.
Right.
And the core argument of the report is that this is the state our host is in.
But why would it be in that specific extreme state? Why push it right to the absolute limit?
Thermodynamics. It all comes down to entropy.
The universe loves a mess.
It absolutely does. I mean,
Right.
think of your bedroom. There's only one way for it to be perfectly, spotlessly clean. Every book aligned, every sock in a drawer. But there are millions, billions of ways for it to be messy.
My bedroom is a testament to that fact.
So, statistically, if you just stumble into a room at random, you are far, far more likely to find a messy room than a perfectly clean one. High entropy states are just more probable. The Narii limit represents the maximal entropy state for a Schwarzschild de Sitter black hole. It is the messiest, most information-rich, most probable configuration possible.
So, our existence isn't just some random accident. We're here because, statistically, a black hole universe wants to be in this configuration. It's the most likely outcome.
It is thermodynamically favored. And when you do the math for this Narii limit, this special case where the horizons merge, you naturally derive that inverse square law. And here's where it gets spooky.
Spooky good or spooky bad?
Spooky precise. We have measured the vacuum energy in our universe. We know its value. It's incredibly tiny, about 1.9 times 10 to the minus 52 inverse square meters.
Which is the whole fine-tuning problem, right? Why is it so ridiculously small? Standard physics predicts it should be huge.
Exactly. But if you take that inverse square scaling law, derived from the Narii limit, and you plug in that tiny observed value for lambda, you can ask, how massive must the host black hole be to produce a vacuum energy this small.
I'm looking at the calculation right here in the report. You plug in 10 to the minus 52.
And the mass that pops out is approximately 10 to the 53 kilograms.
That's exactly the mass we were talking about earlier.
It matches the bag of gold mass requirement perfectly.
Damn, okay.
That is the aha moment of the paper. In the standard model, that tiny number for dark energy is a profound mystery. I mean, scientists talk about needing 120 orders of magnitude of cancellation. It's basically a miracle to get a number that small.
But in this model, it's not a miracle.
It's just geometry. It's a consequence of scale. The cosmological constant is small simply because our host black hole is very, very large. A massive host must have a tiny interior vacuum energy. It's like a seesaw. Heavy host, light energy. Problem solved.
So we don't need a multiverse where we just happen to get lucky and land in the one universe with the right number.
Yep.
We just need to be inside a really, really big black hole, which is the most thermodynamically likely kind of black hole universe to exist anyway.
It replaces cosmic luck with geometric necessity.
Okay, I need a second to process that. We fit in the bag because of topology. And the reason our universe feels so fine-tuned for life is because we're just seeing the interior scaling of a massive, stable object.
That's the argument.
But this leads to the origin story. Standard cosmology says Big Bang, a singularity, infinite density, time itself starts at zero.
And physicists, deep down, hate singularities. A singularity is just a fancy mathematical way of saying our calculator broke. It means the theory has failed.
Yep.
Infinite density, infinite curvature, those things don't exist in nature. They are a sign that your model is incomplete.
So what replaces it? The report talks about a bounce.
A big bounce. To understand this, we have to leave Einstein's standard general relativity for a moment and bring in some of his friends, or rather, people who built on his work. We need something called Einstein-Cartan-Sayama-Kibble gravity.
ECSK, gravity.
ECSK. It sounds like a law firm, I know.
Yeah.
But what they bring to the table is a new geometric quantity.
Which is?
Torsion.
Torsion, as in twisting.
Exactly. Standard GR says spacetime's like a rubber sheet. You put a bowling ball on it, it curves. That's gravity. Simple. But matter, electrons, quarks, all the fermions, has an intrinsic quantum property called spin. In standard GR, we basically just ignore this. We assume the spin of individual particles is too small to have any meaningful effect on the large-scale geometry of spacetime.
But ECSK says it does have an effect.
ECSK says that spin creates torsion. It doesn't curve space, it twists it.
Wait, like wringing out a wet towel?
That's actually a fantastic analogy. Imagine spacetime as a towel. If you lay it flat and put a weight on it, it sags and curves. That's Einstein. But if you grab both ends of that towel and start twisting them in opposite directions,
the towel tightens up, it gets stiff, it resists the twisting.
Exactly. It resists. Now, at low densities, like here in this room or even inside the sun, this twisting effect is utterly negligible. It's far too weak to notice.
But if you crush it down...
If you crush matter down to the densities you'd find inside a collapsing black hole, we're talking densities greater than 10 to the 45 kilograms per cubic meter. The so-called Cartan density, that stiffness of the spacetime towel, becomes a dominant force. The spin-torsion coupling creates a massive, powerful, repulsive force. It's essentially anti-gravity.
So the star collapses, gets smaller and smaller and denser, and then the towel is twisted as tight as it can possibly go.
And it snaps back. The torsion prevents the singularity from ever forming. The collapse halts before it can hit infinite density, and that immense repulsive force drives the matter back out in a violent expansion.
A bounce.
A bounce. So the sequence is, a massive star in the parent universe collapses. But inside the newly formed event horizon, that collapse turns into a massive expansion.
And to us, living on the inside, in that expanding phase, that moment of snapback would look exactly like
the Big Bang. What we have interpreted as the absolute beginning of time was actually just the moment the torsion repulsion kicked in and reversed the collapse.
That is unbelievably cool, and the report mentions this torsion mechanism does one other huge favor for us. It explains baryogenesis.
Right. The big question. Why is there more matter than antimatter?
The classic problem. In the Big Bang, matter and antimatter should have been created in perfectly equal amounts, which means they should have annihilated each other instantly, leaving behind nothing but a universe full of gamma rays. We shouldn't be here.
But we are here. The report argues that this ultra-dense torsion field interacts with particles and antiparticles differently. It's not a symmetric interaction. It affects their decay rates.
It introduces a bias.
A geometric bias, yes. The twisting of spacetime itself at that moment of the bounce naturally favors the production of baryons matter over antibaryons. So we exist because the twist of space-time at the moment of our universe's birth saved us from total annihilation.
So let me recap the theory side of this. We are living in a bag of gold, which allows more mass inside than outside. The sheer size of our host black hole explains why dark energy is so weak, and torsion explains both the Big Bang as a bounce and why we're made of matter.
It's a very clean, unified picture. It ties up a lot of loose ends.
But, and this is the big but, isn't it? Theories are cheap. I can write a theory that says the universe is a giant donut made of glazed dark matter.
Please don't. The peer reviewers would have a field day.
I won't. But the point is, you need proof, you need data, you need to see it in the sky. And this is where the 2026 report pivots from cool math to look at this.
The observational evidence, and they present three main pillars here. The first one is spin.
The universe is spinning.
Well, the standard cosmological principle assumes the universe is isotropic and homogeneous, the same in all directions, no preferred axis, no rotation. But if we are inside a host black hole.
And real astrophysical black holes spin. They're not static, they're Kerr black holes.
Exactly. Conservation of angular momentum. If the parent star that formed it was spinning even a little, the black hole it forms will be spinning like crazy. And if the host black hole spins, that primordial torsion from the bounce should drag the interior spacetime along with it.
Frame dragging.
But on a cosmic scale, this should impart a preferred axis onto our entire universe, a cosmic north pole and a south pole, effectively.
And do we actually see that? Because I feel like I would have noticed if the universe had a north pole.
You wouldn't notice it just looking out the window on a clear night. But the James Webb Space Telescope noticed it. The report heavily cites the massive observational study by Lior Shamir from 2025.
I remember the headlines about that, but break it down for us. What did he find?
Shamir and his team analyzed tens of thousands of spiral galaxies from the JWST deep fields. Now, if the universe is truly random, the direction of galaxy rotation should be a coin flip. 50% should appear to spin clockwise, 50% counterclockwise.
Like tossing a bunch of pennies, half heads, half tails.
Right. But when Shamir analyzed the data, he found a clear multipole asymmetry, a parity violation.
Meaning the pennies were landing heads up more often than tails.
But only in certain directions. If you look one way in the sky, you see a statistically significant excess of clockwise spinning galaxies. And if you look 180 degrees the other way, you see an excess of counterclockwise ones.
That strongly suggests the whole structure is twisting.
It suggests the background spacetime itself has a handedness, a spin bias. The galaxies are just like leaves floating in a river, and their alignment is revealing that the river itself is swirling.
And the swirling river is the rotation of the host black hole.
Precisely. It's the physical imprint of our container.
And that connects to the other JWST anomaly, right? The impossible seeds, the quasar candidate catalog.
Yes. This has been a massive headache for astronomers since JWST first came online. We keep finding these supermassive black holes, quasars, at incredibly early times in the universe. We're talking redshift 6, 7, even higher.
That's less than 1 billion years after the Big Bang.
And they are huge. Billions of solar masses. Standard growth models for black holes say that is impossible. There just hasn't been enough time. You can't start from a small stellar mass black hole and eat that fast.
It's like finding a fully grown 6-foot-tall teenager in a maternity ward.
It's exactly like that, but in the black hole universe model.
The bag of gold.
Remember, the interior mass is decoupled from the exterior. You don't necessarily have to start from zero after the bounce. The report calls them inherited seeds. The collapse mechanism and the non-uniform density distribution inside the bag could allow for massive objects to form almost immediately after the bounce.
So the impossible quasars are actually evidence that the standard start-from-scratch model is wrong.
They're features, not bugs. And get this, the report points out a dipole alignment in the distribution of these seeds.
The dipole again, the preferred axis.
Yes. Two of the most massive and impossible quasar candidates from the QHSC catalog are located almost exactly 180 degrees apart on the sky map.
Back to back.
Like they were lined up along.
The axis of rotation.
The axis. It's another piece of evidence pointing to the same thing.
Huh.
The universe has a large-scale structure, a spin, and an axis that perfectly matches the expected properties of a rotating host.
Okay, that's very compelling. But we have to talk about the elephant in the room. The data that panicked everybody in the cosmology community last year, the DSI results.
The dark energy spectroscopic instrument, this is the third pillar of their evidence and arguably the strongest.
Let's rewind a bit, back to 2024 and 2025. Standard cosmology, the lambda CDM model, relies on the cosmological constant, lambda, and the word constant is doing a lot of heavy lifting there.
That's the whole point.
It means dark energy. The stuff causing the universe's expansion to accelerate should not change, ever. It's a fundamental property of space itself. Its equation of state, W, should be exactly -1, always.
It's the bedrock of the entire model.
But then DSI released its Year 1 and Year 3 data compilations, and the line wasn't flat.
It wasn't flat. They found strong evidence that dark energy is thawing. It's evolving over cosmic time. The equation of state, W, isn't a constant -1. It's changing. We call it the W0WA CDM model now.
I remember the conferences. People were freaking out. The headlines were all, new physics needed, Einstein's constant isn't constant.
Because if dark energy changes, the standard lambda CDM model is fundamentally broken. But the authors of this BHU report, you can imagine they were probably popping champagne.
Why? Why does thawing or evolving dark energy fit the black hole model so perfectly?
Think about the host again. We already established that the host black hole sets the value of the interior vacuum energy lambda via that inverse square scaling law.
Right. Lambda depends on the host's mass.
Exactly. Now ask yourself this. Is the host black hole a static object? Is it just sitting there, frozen in time in its parent universe?
No, of course not. It's a black hole. It's in a parent universe full of stuff. It interacts.
It eats, it accretes gas and dust. It might merge with other black holes or stars. It's an active astrophysical object.
So the host mass, M host, is probably increasing over time.
And if M host goes up, what happens to lambda in an inverse square relationship?
If the bottom of the fraction gets bigger, the total result gets smaller.
Exactly. As a host grows by accreting matter, the vacuum energy inside its bag of gold interior must decrease.
So the thawing or weakening of dark energy that DSI observed, that's just us from the inside watching our host gain weight.
That is the interpretation. We're observing the relaxation of our own interior geometry as our container grows. We are, in a very real sense, measuring the metabolism of our host.
That is a visceral image. We're literally inside the belly of the beast, and we can tell when it's feeding time because our dark energy graph wiggles a little bit.
It completely recontextualizes what dark energy is.
Yeah.
It's not some magical, unchanging constant of nature. It's a state variable. It's dynamic. It depends on the environment our universe lives in.
So DSI didn't break physics. It just proved that we are part of a larger dynamic system.
That is the argument. And it fits the data beautifully. The measured rate of decay in lambda from the DSI results matches the expected accretion rates for a supermassive black hole of this calculated size.
Okay, I think I'm convinced, or at least I'm thoroughly shaken. We have the topology that fits the mass. We have the scaling law that fits the energy. We have the torsion that explains the bounce in our existence. We have the cosmic spin that matches the galaxies. And we have the evolving dark energy that matches the host's growth.
It's a full house, as they say. It addresses a whole suite of problems at once.
So let's zoom out. What does this all mean? Philosophically, the report brings up Smolens's work again near the end. Cosmological natural selection.
Right. If this model holds up, it completely changes our place in the cosmos. Smolens's idea was that universes reproduce, and black holes are the reproductive organs of a universe.
That's a weird image, but go on.
A universe forms, it lives, it creates black holes. Each black hole, through this bounce mechanism, creates a new baby universe inside it. That baby universe inherits the physical laws of its parent, but with slight mutations introduced by the extreme conditions of the bounce.
It's Darwinian evolution. Descent with modification, but for entire universes.
Exactly. So universes that are, for whatever reason, good at making black holes, universes with the right constants for stars to form, for gravity to work, for carbon chemistry to exist, those universes will have trillions and trillions of offspring.
And universes that are bad at it, empty voids with the wrong physics, will just die out, having no offspring.
And our universe is really good at making black holes. They're everywhere. We are a veritable black hole factory, which suggests we are not a random accident. We are the product of eons of cosmic evolution. We're a dominant species of universe, fine-tuned by natural selection to be this way.
And the Nari limit supports that too, right? The idea of being in the most probable state?
Yes. We find ourselves in a maximal entropy state. It's the most likely configuration to arise from a successful evolutionary lineage.
It makes the universe feel less like a cold, random, meaningless void, and more like
Yeah.
life, a living, reproducing chain of existence.
It's a much more organic view of cosmology, absolutely.
So what's next? This is a huge report, but it's still just a report. How do we prove it for real? How do we put the final nail in the coffin of the old model?
We need more precision. The report points to the next generation cosmological surveys,
Yeah.
the Euclid Space Telescope and the Vera C. Rubin Observatory's LSST survey.
And what are they looking for specifically?
They need to tighten the error bars on the decay of lambda. The DCA data is good, but we need to track that evolution of dark energy with even greater precision across cosmic time. If the curve of that evolution perfectly matches the accretion curve of a black hole, that's a smoking gun.
And gravitational waves, you mentioned them earlier.
That's the other big test, the LISA mission, the Laser Interferometer Space Antenna.
The giant space-based gravitational wave detector.
Right. The old Big Bang model, standard inflation theory, predicts a very specific background hum of gravitational waves left over from the first moments of the universe. They're called primordial tensor modes.
But the bounce model is different.
The bounce mechanism in ECSK gravity actively suppresses the production of those specific modes. It should be very quiet in a specific frequency range that LISA is designed to listen to. So if LISA turns on in the 2030s and hears silence where inflation predicts a loud noise,
That's the signature of torsion.
that's the signature of the bounce.
It's just incredible that we might actually know the answer, one way or the other, in our lifetimes.
We are on the precipice of a genuine revelation in our understanding of everything.
Before I go, I have to ask the question, the one that's been gnawing at me since I read the conclusion of the paper.
I suspect I know which one you mean.
If we are inside a black hole, and we know from Stephen Hawking that black holes eventually die, what happens to us?
Hawking radiation.
Right. Stephen Hawking proved that black holes aren't truly black. They have a temperature, they leak, they radiate energy away into their parent universe, and eventually they evaporate.
Slowly but surely. Very, very slowly.
So if our host is evaporating particle by particle into its parent universe, does that mean we are leaking out? Is our universe disappearing?
It's the ultimate provocative thought, isn't it? If the host loses mass, its event horizon, the throat of the bag shrinks.
But the bag inside is huge and we're in it.
There is a deep debate in the theoretical community about what would happen. Does the interior spacetime pinch off and become its own independent, orphaned universe? Or does the information, the gold that makes up our cosmos, slowly leak back out into the parent universe over unimaginable timescales?
Are we? Are we fading away?
In a sense, we might be slowly returning to the parent.
Yeah.
But you have to remember the timescales involved here. For a black hole with a mass of 10 to the 53 kilograms, the evaporation time is...
Please don't tell me it's tomorrow.
It's roughly 10 to the power of 100 years. A Google years.
Okay, so longer than the current age of our universe, by a lot.
By orders of magnitude that are literally impossible to comprehend. We are safe. The bag of gold is a very, very secure vault for the foreseeable future.
That helps. A little. It's still a strange thought.
But does change your perspective on the night sky, doesn't it?
It really does. And I think that's the thought I want to leave everyone listening with. Tonight, if you can, go outside. Look up at the stars. Usually you feel small. You feel like you are on a tiny rock looking out into an infinite, cold, uncaring void.
But if this report is right,
If this is right, you aren't looking at a void. You are looking at the internal structure of a vast, ancient, protective shell. We are the gold in the bag. We are the complex, vibrant, living interior of something much larger, much older, and much, much stranger than we ever imagined.
we are the hidden heart of a giant.
Exactly. This has been the deep dive into the black hole universe. Thanks for letting us completely break your brain today.
It was a pleasure, as always.
We'll see you next time, and keep looking up.